Thank you. So thanks to the organizers, especially for being willing to accommodate another online talk, and to the audience members for tolerating another Zoom talk. So what the work I'll tell you about will be, I expect it to be posted shortly, and it's joint with Taryn C, who's at Macalester. Okay, so today I'll be discussing, just for concreteness, I want to say the operators that I'm discussing and give them names. So we'll be describing the spherical extension operator. And so if I need to disambiguate, I'll have a subscript S next to that operator. But since this is the primary operator I'll describe, it'll mostly be script E. And this is just the integral on SD of, I have some function F that's living on the sphere. And I correlate this with waves with frequencies given by the sphere. And so the sphere is SD, so the d-dimensional sphere, and our d+1. And so for this extension operator gives me a function on our d+1. And this is also connected with the parabolic extension operator. So I take a function g, which I think of as living on the paraboloid. So half, whoops, that's not what I meant to do. Half c squared xc, but it's simpler to just parameterize this g of xc integrated with respect to dxc. And now I have, again, my point x is in our d+1 and my paraboloid is d-dimensional. And there's a natural connection between these two operators, which also explains the factor 1/2 here, and that is that the square root of 1 minus norm c squared is roughly 1 minus half the norm of c squared for c really small. And this factor 1 here is actually going to play an important role in the analysis later on. So of course, a major open question is for which P and Q do these operators extend as bounded linear operators from LP to LQ? And so heuristically, we think of this as the question of when LP smoothness leads to LQ decay. So the larger, again, the larger P is on this side, the nicer our function has to be to still live in LP. It can't have spikes that are too large. On the other hand, the smaller Q is, the faster the decay has to be of this extension over here. And so the game is to try to lower Q as much as possible at the cost of raising P. So I'm not going to tell you anything new about this open question unless I tell you something that's wrong, which I hope that I won't. So there are 4 questions that we're interested in this talk. So let's suppose that this extension to the sphere has a finite LP-LQ norm, and we're going to call that S for sphere, P to Q. So what this tells us immediately is that the norm of the extension of a function f in LQ is less than or equal to this operator norm times the norm of f in LP. And so the questions all relate to what happens when we try to reverse this inequality and ask for which functions f can this be reversed. And so the first of that question is, does there exist a non-zero function f in LP such that we have equality here? So the norm of the extension of f in LQ is equal to the operator norm times the norm of f in LP. So the question of whether extremizers exist for bounded linear operators, this is of course trivial if LP is replaced by a finite dimensional Banach space because the unit sphere is compact. However, in infinite dimensional Banach spaces, this question becomes interesting. And for some bounded linear operators, there do exist extremizers. For some, there do not exist extremizers. And I guess for most of them, we don't know the answer. Now, a different question, again, A different but related question is, what are the properties of functions f for which, instead of having equality here, we just have that the norm of the extension operator is greater than or equal to some constant times the norm of f in LP. Alternately, one can replace this constant C0 by instead 1 minus epsilon times the operator norm. So such a function here would be called a near extremizer. And of course, this condition becomes stronger as epsilon gets smaller. And so we'd expect to have more information. Finally, one can ask, what is the connection between this quantity S, the operator norm of the spherical extension operator, and the operator norm of the parabolic extension operator. And I'll denote that operator norm by P for paraboloid. Okay, so now I'll say a bit about our setting. And so the overview of the talk is that we can say something, in a lot of cases it's a very qualitative something, about all of these questions, but only for P and Q in a certain range. And so I'll describe to you what that range is in a moment. But first I want to describe some background for the adjoint restriction conjecture. So first, it's known that SPQ is finite for, the conjecture, excuse me, is that SPQ is finite for Q strictly larger. And so in this usual diagram, that means that Q is living below this dotted line. So Q larger than 2D plus 1 over D, and Q greater than or equal to. So again, Q is now below or on this solid line here, D plus 2 over dP prime. This is called the parabolic scaling line. And so I've indicated this region with black dotted lines or solid lines. There's been substantial progress on this conjecture, but it's still open in all dimensions greater than or equal to 2. So let's let KD, and this is the region bounded by blue lines, denote the known region of boundedness. The conjecture is solved when D is equal to 1, so the blue lines and the black lines correspond. But in all of the other dimensions, it's open. And the records are due to Wang, Guth, or Hickman-Rogers, depending on the dimension. And roughly, you get a region that looks a little bit like this. So you have a horizontal line, and then a slightly slanty line that goes down to the parabolic scaling line. And then in some range, this lives along the parabolic scaling line. So the hypothesis that we make in this talk is, first of all, that Q is finite. That turns out not to be a really significant hypothesis, as we'll see in just a moment. That Q is strictly larger than P. That hypothesis is extremely important for us. And the last one is that PQ is in the relative interior of the region where the bounds are known inside the conjectured region. And we're going to call this AD for the admissible region. And this is shown in red. And of particular note is that the red region can include the parabolic scaling line. So now I want to give a sampling of the prior results on this operator. This does not cover all of the results, but those that I could fit on a single slide and that were most closely related to the results that I'm going to describe for you. So the earliest result is due to Fanelli, Vigilia, Vega, and it says that extremizers exist along this red line when P is equal to 1/2, excluding the endpoint here on the parabolic scaling line. So Q equals 2D plus 2 over dP prime. And the methods here are to use a sort of concentration compactness methods and profile decompositions. It's also been shown that if D is equal to 1, so we're going to concentrate now at the endpoint here that's shown as a blue dot. And so this is the case when P is equal to 2 and Q equals 2D plus 2 over D. And that corresponds to the Stein-Thomas inequality. So it's known that there exist extremizers when d is equal to 1, and also when d is equal to 2, that's due to, so when d is equal to 1, this is due to Schau. When d is equal to 2, it's Kristen Schau. And it's also known that they're constants in those 2 dimensions, and this is due to Fourier. For all values of all dimensions d, it's also known that extremizers exist when S, the spherical operator norm, is strictly greater than some constant times the parabolic operator norm. And we'll say a little bit more about this constant later on, and it relates to some of our results. Also of note is that there's a nice little argument using Fatu that shows that, again, so on the scaling line, SPQ is less than or equal to this constant. So, and this result is due to Franck-Liebsabin. Okay. It's also known that there exist extremizers and they're constants when Q is an even integer plus some other conditions, and this is a result of Carniero and Oliveira S. Silva. And I've drawn some of, again, the eraser. I've drawn some of these lines here. Okay. So now there are a couple of elementary results that I want to make you aware of. So if Q is equal to infinity, then it's elementary to show that constants are the unique extremizers, except at the case when P is equal to 1 and Q is equal to infinity. And in that case, any non-negative function is an extremizer. And both of these results can just for simple applications of Hilbert's inequality. So what's new that we'll describe in this talk is the rest of the triangle that's shown in green. So along the parabolic scaling line, and then below the parabolic scaling line, and also below the line P equals Q. Now, I've drawn it to fill in the entire triangle. However, some of the results are conditional and would rely on further progress toward the extension conjecture. So I'll start first with the results that are new regarding extremizers. And again, so everything that I'll say here is joint with Taryn block. Our first theorem is that if we are in the interior of the green region, so Q is both greater than P and also greater than this parabolic scaling exponent, and PQ are in this admissible region, so the interior of the known region, then extremizers exist, and normalized extremizing sequences have convergent subsequences after we allow for modulation. The second theorem is that if we're along the parabolic scaling line, and again in the admissible region, then extremizers exist, and normalizing extremizing sequences have convergent subsequences after modulation, provided our spherical norm is strictly greater than some threshold times the parabolic norm. Now, in dimensions 1 and 2, this threshold, this strict inequality is attained when P is equal to 2, and one can deduce from that that it's a strict inequality when P minus 2 is sufficiently small. And thus, if we're on the parabolic scaling line, and I'll show you this in the picture, and we are sufficiently close to this blue dot, then extremizers exist. Okay, so we'll prove these results by proving something that is a bit more general, and that is a profile decomposition. Oh, sorry. Let me say a little bit about this threshold constant, beta PQ. So it is this strange looking thing. So it's the minimum of P prime and 2 times the gamma function of Q plus 1 over 2 times the square root of pi divided by the gamma function of Q plus 2 over 2 to the 1 over Q. And it arises as an upper bound for this functional psi of t, which is the average in the LQ with respect to the average norm of 1 plus t e to the I theta divided by 1 plus t to the p to the 1 over p. And this is a generalization of a quantity that arose in the work of Franck and Savin. So now our results on extremizers are obtained by via more general results, and these are profile decompositions. Now, our profile decomposition is going to apply to a sequence of function, a bounded sequence of functions in LP. And there are two different stages to this decomposition. The first is a frequency decomposition, and the second stage is a spatial decomposition of these sequences. We'll state them as three separate results just to simplify matters, but these can be taken together to produce a fairly robust decomposition of these sequences. Okay, so let's suppose that we have a bounded sequence in LP of the sphere. Then along a subsequence, I have that I can decompose my function Fn as a sum of pieces, so capital F in J, plus a remainder term R in J. And so the functions in this sequence, in this decomposition, need to have a few properties, or the decomposition is meaningless. So the first of these is that these functions exhibit really good LP orthogonality. I'm going to write it in the following way. So this is saying that my LP norms don't interact with one another. This is a fancy expression of a much simpler fact, which is that in this decomposition, these pieces have disjoint supports. The second condition is a bit stronger. It says that when I apply the extension operator to these pieces, then they don't interact very much with one another, at least once I take the limit as n goes to infinity. And so this, I can compute this LQ norm of the extension of Fn by separately computing the LQ norm of the extensions of these pieces, at least once I take that limit. Now these R and J's are small in the sense that when I let n go to infinity and then let the order of my approximation go out to infinity, I have something whose extension is very small. And finally, these pieces have good frequency localization in the following sense. So if I'm looking, so I want to think of Fn0 as my scale 0 piece. So this is the piece that is well localized to the whole sphere. And so what that means is that morally, I can think of Fn0 almost as being a bounded function. So the sense in which it's almost a bounded function is that if I multiply it by the characteristic function of the set where this is bounded, so bounded by some constant m, then that's going to account for most of my extension. And I express it in this way. And what's important to note here, so this condition that the limit as m goes to infinity, the limit as n goes to infinity of the extension of this piece is equal to 0, that would be relatively simple to prove if I were to exchange this limit with this one just by the dominated convergence theorem. However, the fact that the limit as m goes to infinity is on the outside means that this has real content. Okay. So now I'm going to move to some smaller scale pieces. And so the way that the cartoon here is I'm going to think of these F and J's when J is smaller. I'm going to think of them as being really localized to lambda and J neighborhoods of antipodal pairs. So omega in J and minus omega in J in the sphere. So I have my sphere, and I have a line that's through the sphere. And so I have omega in J here and minus omega in J here. And so the sense in which this is well localized to that scale is morally f and j can be bounded by an LP normalized characteristic function near these poles. Okay, so I'm going to, the way that I write that quantitatively is I take the set of omegas that are not close enough to either one of these poles, and I also take the set of omegas where f in j is really big, and I throw all of those guys away. If I take the extension of what's left, then I get most of f in j. And again, it's critical here that the limit as m goes to infinity is on the outside and not on the inside. Okay, and so finally, with this notation in place, I can go back and I can state a more intuitive and geometric version of 2, which is that when j is not equal to k, so if j is not equal to k, I'm going to have 2 places where my function is concentrating. So let's say that this is omega n k and minus omega n k. So there are one of 2 things happens. So either the ratio of the scales goes to infinity, and they are the 2 regions orthogonal in that sense. So one is big and one is really small, or else the scales are the same, but the distance between these 2 lines goes to infinity after I rescale by the common radius of those neighborhoods. So we'll say a little bit about the proof in a moment, but for now I want to describe some of the corollaries and also the shortcomings of this frequency decomposition. So the first corollary is that if I have an LP normalized sequence and the norm of the extensions doesn't go to 0, then it's really just a few pieces, and we can bound the number using C0. So just a few pieces are contributing most of the extension, and the rest I can think of as error. The second corollary, we have a stronger result in the extremizing case. So if the norm of Fn and LP is identically 1, and the norm of the extensions are going to the operator norm, then one piece contributes most of the extension and also most of the LP norm of the function. So a sketch proof of the corollary, so this very strongly uses the condition that Q is strictly larger than P, as we'll see. So my operator norm is equal to the limit of the norms of the extensions of these well-localized pieces because of the LQ orthogonality. This, of course, is then bounded by, I just bound each of these using the operator norm. So this is the operator norm times the sum of the LP norms raised to the Q. Now, by Helder's inequality in little LP, this is bounded by again, so I just retain the operator norm here times the sup on n of the excess LP norm. So that's the norm of f in j to the q minus p times something that I've already seen sums to 1. And this is bounded by 1. Moreover, if equality holds, each of these inequalities has to be equality. And so this says that here, everybody has to be an extremizing sequence. All of the f and j's have to be extremizing. And here, I find out that there really has to be only one f and j, and that it has norm going to 1. Now, a shortcoming of this result is that it takes my sequence Fn and it shows that the absolute value is bounded by a sum of pre-compact sequences, almost modulo scaling and rotation. However, the Fn's might oscillate And so since the FNs may be oscillating, their extensions are not well localized. So I'll give you an idea of how this is proved. There's an easy case, and that is when I am below the parabolic scaling line, and turns out to be a simple consequence of Hölder's inequality, that we have the piece that is well localized to the sphere plus a small error. And here small means that its extension is small. The harder case is when we live on the parabolic scaling line. And so the decomposition has two steps. So the first step is to break my function into small chips. And the way that this is done is following an argument established by Bego-Vargas. So the bilinear restriction estimate of tau plus the bilinear to linear argument of tau, Vargas, and Vega gives us an alternate way of bounding the extension operator. And so this is going to be something that is smaller than the LP norm. And so what I do is I can find dyadic caps tau, such that when F is multiplied by a characteristic function of tau, and then I restrict F to be, again, so LP normalized according to this cap, then the soup on those taus is, well, this is smaller than the norm of F and LP. And so I have some cap that's contributing a big part to the norm of F. And so the idea is that I have now a characteristic function involved in this definition. So I'm going to find the biggest tau over here. I'm going to just chip that off from my function F. That's going to leave me some remainder. I'm going to do that again, find the biggest tau, chip that piece off, and continue. And eventually I'm going to be left with no function, but more importantly, I'm going to be left with no extension, and I can make this quantitative. The good news is that the pieces are LP orthogonal, and the extension of their remainders tends to 0. The bad news is I've taken these chips kind of randomly. They don't necessarily have anything to do with one another. They might be pretty similar to one another. They might be really different. And so there's no LQ orthogonality. So what we do to regain the LQ orthogonality is we sort the chips into chunks. And the idea with the chunks is that we want to think about putting together the caps tau that are close to one another in the same pile, and in different piles, we're going to put the chips tau that are moving apart from one another as n goes to infinity. Okay. So now we turn back to the shortcoming of the frequency decomposition, which, if you'll remember, has to do with the fact that we don't have control over the oscillations. And so first I'm going to describe a further decomposition of the scale 1 term. This is what I had called Fn0, so the piece that was well localized to the sphere. And so the theorem is that if I have a bounded sequence in LP that has good localization to the sphere, in the sense that when I throw away, whoops, there should be a characteristic function here. This is. When I throw away the parts of Fn that are big, the extension is small. If I have that condition, then along a subsequence, I have a nice decomposition of Fn into modulations of pieces with no n dependence. So there's no subscript n. This is just depending on j, the level in the decomposition, plus a remainder term. And so these phi j's are going to be in little LP. And I've got a lot of nice properties. So the first of these is that I have good LQ orthogonality. So the norm of the extension of Fn and LQ was well approximated by the sum of the extensions of the phi j's and LQ to the Q, and then the remainders. And so this LQ orthogonality has a more physical interpretation or more geometric interpretation, which is that the x's that are governing these modulations are moving apart as n goes to infinity. Next, these errors are small in the sense that their extensions are small as n and then j go to infinity. We also have a sort of LP semi-orthogonal. And so these two both look like what we had before. Now, before we had really nice LP orthogonality and in a really strong sense that the supports were disjoint from one another. Now we have a weaker condition, which is a sort of semi-orthogonality. And that is that the LP norms of the main part of F, this is bounded by the sum from j equals 1 to j of phi j and LP to the minimum of P and P prime. And then on the other hand, if I look at the sum of the norms of the phi j's in the larger of P and P prime, this is bounded by the norm of the FNs. And then finally, the phi j's come from taking weak limits of my sequence Fn. And so what I just want to point out is that in both of these inequalities in this part, I'm taking the weaker of the, I'm taking the little LP norm on the appropriate side that makes this inequality weaker. These two coincide when, of course, P is equal to 2, and we have a much stronger condition in that case. Well, this result has a couple of corollaries. So the first is that if Fn is bounded with good scale 1 localization, and the extensions aren't too small, then there are few spatially localized pieces contributing most of the extension of Fn. And in particular, if Fn is scale 1 localized and extremizing, then one piece is contributing almost all of the extension of Fn and Fn. And so in particular, corollary 2 implies, can be used to show that extremizers exist if we are strictly below the parabolic scaling line. Another consequence of this, in a more qualitative, stated in a more qualitative way, is that there are two options for normalized extremizing sequences. So either they have convergent subsequences, or else, so that's the case where everything is in Fn0 and well localized to the sphere, or else they are concentrating at incipital pairs of points. So I want to give an idea of the proof of this theorem and sort of explain what is different and new from what had come before. So an idea of how the proof goes. So the first step is the case when P is equal to 2. And so here I have that P is equal to P prime. And so those two inequalities that I showed you are sharper. But in fact, we have even better results than the natural generalization of what I had written down. And so this is roughly because weak limits are a lot friendlier in Hilbert spaces. So if I have a sequence of functions and it has a weak limit and I subtract off that weak limit from the sequence of functions, it decreases the norm in a Hilbert space, but that doesn't work if we're outside of the context of Hilbert spaces. And also this profile decomposition when P is equal to 2 is essentially already known, although it wasn't precisely written down as such. Now the second step is I want to try to apply the result from the P equal to 2 case in the case of general P. And so what we can do is we can take our function Fn and we can truncate it we've been told that this is providing most of the contribution to the extension. This is bounded in L2, and so we can apply the L2 profile decomposition. And that leads to a decomposition here. And so then one can show that this decomposition arising in the L2 profile decomposition actually obeys all of the properties that we want it to obey for the LP profile decomposition. Now, unfortunately, when I truncate like this and put what's left in L2, this has a really bad bound in L2, and as m is going to infinity, my LP approximation gets better, and this is a better approximation of my function fn, but also the L2 norm blows up. One question that I just want to bring up here, so what's important when we allow m to go to infinity, one reason that having this inequality hold with less than or equal to instead of a less sim, so one reason this is useful is that it makes it easier to let m go to infinity. But it brings up a related question, which is, so proving this inequality uses the curvature of the sphere, and it could be interesting to know whether one could prove this with different exponents here instead of just, and in particular, if one can avoid the use of p prime. Now, the third step is we really want to remove this m dependence, but there are two problems. So one I've already mentioned, that the L2 norm blows up as m goes to infinity. The other one is that a range cutoff like this, so this is depending on the function and is not just some fixed characteristic function, this doesn't cooperate very well with taking weak limits. And so I want to describe step 3 in a little bit more detail. Now, in the extremal case, which I had considered in previous work regarding the existence of extremizers for extension from the paraboloid, we have one big piece and then a bunch of small errors. And so the main goal is just to show that the x and m, so these are the modulation terms from the big piece, that they don't run away as I send m to infinity. Okay. So now, since I only have a single piece, I can pick a pretty good approximation xn m0. I can modulate everything so that xn m0 is constant, and then I just need to make sure that this doesn't go to infinity as m goes to infinity, and so it's not too complicated. In the non-extremal case, I've got a lot more pieces. They don't come in any necessary order. They're all running around. It's kind of chaotic. I am not seeing exactly what's going on because everything is mediated through the extension operator. And so I have this image which is stuck in my head, which is of puppies under a blanket. So what we have again is our function fn m, and we have a profile decomposition for this. But what we want is to erase all of the m's so that fn is decomposed as a sum of modulated phi j's plus a remainder term. And so the cartoon that's in my mind when I think about this is, I think that morally I have, let's just draw everything in one dimension. I have my real line, and I have some points, xn1, xn2, xn3, and at each of these points I have a puppy. So here's phi 1, here's phi 2, and here's phi 3. And these are kind of running around and running apart from each other. So now I'm going to throw a blanket over the whole thing. And so this blanket sort of corresponds to taking my truncations in m and approximating. And so what I see is just what's above the blanket. Okay, but unfortunately, this is not necessarily what I see, because maybe my pieces are misordered. Or worse, maybe the wrinkles in the blanket make me think that possibly there's some other puppies. And I have to be able to discern what's going on underneath. But the idea roughly is that we identify where we're seeing large pieces, and the large pieces really have to correspond to a puppy. And there can't be too many large pieces by using bounds on, by using the LP almost orthogonality. And so then we proceed roughly as before in the extremal case. So the last step is to provide a further decomposition of those sequences that are concentrating antipodally. And so the theorem is that if I have a sequence Fn and LP that's frequency localized to about the north and south pole to some scale lambda n going to 0, and so this is in the quantitative sense that I described before, so this is almost bounded by an LP normalized characteristic function, then along a sequence, I have a decomposition. And so what this decomposition looks like is I have modulations of these functions g and j. And what are the g and j? These are rescalings of fixed functions. This is independent of n on Rd plus some remainder term. Okay. And so the properties that all of these have are, I have LP almost orthogonality that looks roughly like it did before. I have LQ orthogonality, which says that, again, I can estimate the extension of Fn by the extension of G and J. And whoops, that's the extension of the remainder. Plus, and in addition, so the sort of geometric interpretation of the LQ orthogonality is that parabolic dilations of these modulating terms, x and j, are moving far apart as n goes to infinity. The error terms here have small extension. The phi j's arise as weak limits after modulations and dilations of the original Fn. And finally, so these phi j's, these are LP functions on Rd. And here we see our approximation by the parabolic extension operator. So the extension of the G and J minus the parabolic extensions of the phi and j's goes to 0 after I rescale and modulate appropriately. So now, because of the fact that the sphere is approximated by 1 minus half norm c squared, I'm going to get this extra modulating factor. And it's going to oscillate very, very fast. So lambda n is going to 0. And so this is something that's going to infinity times x1. And so morally, this is oscillating so much faster than this function that it's almost independent of this function. And so I can morally think of this as being, instead of plus or minus e to the I lambda n squared x1, as e to the plus or minus I theta, where theta is sort of a random variable uniformly distributed in 0 to 2 pi. So the consequence of this result, so the first corollary, is that if I have a normalized sequence and it's extremizing, and the sequence is concentrating near the north and south poles, then the operator norm for the spherical extension is bounded by something that looks like this. And so one can see where this functional psi came in from earlier. So I can think of this as t, and this is t. And I can think of this as, you know, this is a separate s and this is an s, but then I can factor out that s. And so I end up with beta pq times the parabolic extension operator norm. The second corollary is that if p is larger than 2, beta is not just an upper bound, but the maximum of that quantity psi from earlier. So if p is larger than 2 and q is equal, the parabolic scaling guy, and we're in the admissible region, then concentrating extremizers have to concentrate evenly to parabolic extremizers. And so I'll close with just a list of questions. So one is what happens in the region where Q is less than or equal to P. So there convexity tools don't really apply. However, there are some results that are known in very special cases here. The next question, of course, is who are the extremizers? Everybody thinks that they're constants, but showing that seems like it would be hard. And it would have some further consequences. And then finally, there's just the question of what is the maximum of this quantity that arises in the operator norm, and where is it attained? And the question is for this in the region when 1 is less than P, is less than 2, is less than Q. Okay. And so I'll close there. Thanks, everybody.